In this episode, we shift from preventing data from leaving the organization to protecting the data itself so that even if it is seen, intercepted, or stolen, it is not easily understood or used. That is the basic idea behind data encryption, and it is one of the most important protection concepts for anyone studying for the Certified Information Systems Auditor (CISA) exam. Encryption changes readable information into a form that is not useful to unauthorized people, and it does that by using rules and keys that control who can turn the protected data back into something meaningful. For a beginner, the topic can sound mathematical or distant, but its real purpose is very practical. Organizations rely on encryption because data travels across networks, sits on devices, moves into backups, and passes through many hands and systems during normal business operations. Once you understand that information is constantly exposed to risk whenever it is stored or moved, encryption starts to look less like an advanced specialty and more like a basic way to preserve confidentiality and trust. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A simple way to think about encryption is to imagine writing a message in a form that only someone with the right secret can read. The readable version of the information is often called plain text, while the protected version becomes an unreadable form that only appears meaningful again when the correct process is applied. That process depends on a key, which is the information that controls how data is locked and unlocked. The key idea for learners is that encryption is not about hiding the fact that data exists. It is about making the content unusable to people who do not have authorized access. If an attacker steals a file, intercepts traffic, or copies a backup, encryption helps make that captured information far less valuable. Without the proper key, what they obtain may look like noise rather than business records, customer details, or financial data. That is why encryption is so often discussed in connection with laptops, mobile devices, databases, cloud storage, and network traffic, because those are all places where exposure can happen even when other controls are present. It also helps to separate encryption from a few other ideas that beginners often mix together. Encryption is not the same thing as simply protecting a file with a password, although passwords may be used to control access to encrypted data. It is also not the same as encoding, which usually changes data into a different format for compatibility rather than security. Likewise, encryption is different from hashing, which transforms information in a one-way manner and is often used for integrity checking or password storage rather than readable recovery. These distinctions matter because the exam and real audit work both expect you to understand control purpose, not just recognize familiar terms. If an organization says it protects sensitive data, an auditor needs to know how that protection actually works and whether it supports confidentiality in a meaningful way. Calling something protected does not make it protected. Real encryption depends on sound methods, strong keys, appropriate use cases, and good surrounding controls that keep the protection from being undermined by careless implementation or weak management. One of the most useful ways to organize the topic is by thinking about where the data is at the time protection is needed. Data at rest refers to information stored on devices, servers, databases, removable media, or backup systems. Data in transit refers to information moving across networks, whether internally or across the internet. Some discussions also include data in use, which refers to information being processed by systems or accessed by users. Each state creates different concerns. A stolen laptop containing customer records is a data at rest problem. An intercepted connection between a user and an application is a data in transit problem. Sensitive information visible during active processing may raise data in use concerns. Encryption can support protection in all of these areas, but not always in exactly the same way. This matters because an organization might do a decent job protecting stored data while leaving network traffic weakly protected, or it might secure online communication while forgetting that backups and portable devices also carry large amounts of sensitive information that remain vulnerable without similar attention. When people first hear about encryption, they often assume it is one single method, but there are actually different approaches depending on how keys are used. One important model is symmetric encryption, where the same key is used to encrypt and decrypt the data. This approach is generally efficient and useful when large amounts of information need protection. The challenge is that both sides must have access to the same secret key, which creates a key distribution problem because that key itself must be protected from unauthorized disclosure. Another model is asymmetric encryption, where one key is used to encrypt and another key is used to decrypt, or where related keys are used for secure exchange and identity functions. This model helps solve certain trust and communication problems, especially across open networks, though it can be more complex and resource-intensive. A beginner does not need to master the mathematics behind these methods to understand the high-level difference. What matters is recognizing that encryption choices affect performance, usability, trust relationships, and the way secrets are managed across systems and users. Because the title of this lesson is Data Encryption rather than pure cryptography, it is especially important to keep the focus on business protection rather than abstract theory. Organizations encrypt data because they want to reduce the risk that unauthorized people can read important information. Customer records, legal documents, payroll information, health data, strategy papers, authentication secrets, and financial transactions all become far less useful to an intruder when encryption is applied correctly. This is why you see encryption used in web sessions, mobile devices, payment processes, remote connections, cloud platforms, and backup storage. The protection becomes especially valuable when data leaves a tightly controlled environment and enters one where physical possession or network access can no longer be treated as trustworthy. If a phone is lost, a portable drive goes missing, or a storage copy is exposed in the wrong place, encryption may be the difference between an inconvenient event and a reportable incident with serious legal, financial, and reputational consequences. Its purpose is not cosmetic. It changes the impact of exposure. Still, encryption has limits, and understanding those limits is a major part of understanding the topic correctly. Encryption protects confidentiality, but it does not automatically decide who should be allowed to access data in the first place. That is still the role of access control, identity management, and governance. It also does not guarantee integrity, availability, or correct business use all by itself. If an authorized user misuses data, encryption may not stop that misuse because the user already has the ability to view the information legitimately. Likewise, if keys are stolen, poorly protected, or shared too broadly, encryption may exist on paper while offering much less real protection than leaders assume. Another common misunderstanding is the belief that encryption solves every data security problem. It does not. An organization still needs classification, monitoring, backup, incident response, secure development, vendor management, and many other controls. Encryption works best as part of layered security, where it reduces harm if other barriers fail rather than being treated as a magical substitute for the rest of the control environment. The mention of keys leads directly to one of the most important truths in this subject. Encryption is only as strong as the management of its keys. If the keys are exposed, poorly stored, improperly shared, or never changed when circumstances require it, then the organization may be protecting data in theory while quietly weakening the protection in practice. Key management includes generating keys securely, storing them appropriately, limiting who can use them, replacing them when necessary, and retiring them when they are no longer needed. It also includes making sure backups, recovery procedures, and responsibilities are handled carefully, because losing access to a necessary key can make important business data unreadable to the organization itself. That creates a different kind of risk, where confidentiality may be preserved but availability is harmed. For auditors, this area often matters more than whether a specific encryption method sounds impressive. A strong algorithm can be undermined by poor key discipline, while a well-managed environment supports more dependable protection. In many real-world reviews, weak key handling is where the practical control failures begin to appear. Another important concept is that encryption decisions should follow data sensitivity and business need rather than habit alone. Not every piece of information requires the same level of protection, and not every system carries the same risk if exposed. This is why organizations usually connect encryption decisions to classification and risk assessment. Sensitive personal information, confidential business records, and highly regulated data often require stronger or more consistent protection than public or low-impact material. The goal is not to encrypt everything blindly without understanding purpose, though some organizations may choose broad protection strategies for simplicity and consistency. The better mindset is to ask which information would create significant harm if exposed, and where that information exists, moves, or is stored. That helps leaders choose sensible protection points and avoid gaps. From a CISA perspective, this matters because audit work often focuses on alignment. The question is whether encryption has been applied where the risk justifies it, whether exceptions are controlled, and whether the organization can show that its decisions reflect thoughtful governance rather than random technical preferences. Data in transit deserves special attention because many beginners underestimate how often information moves across paths the organization does not fully control. When users connect to applications, send messages, upload files, or synchronize data between systems, that traffic may pass through networks where interception is possible. Encryption helps protect those communications so that even if the traffic is captured, the content is not easily readable. This supports confidentiality and helps preserve trust between users, systems, and services. It is especially important in remote work, public networks, third-party connections, and internet-based business activity, where organizations cannot assume the path between 2 points is safe just because the connection is routine. At the same time, encrypted communication introduces operational considerations, because protected traffic may require careful monitoring approaches, proper certificate handling, and attention to configuration. The high-level lesson is that movement creates exposure, and encryption is one of the main tools used to reduce that exposure. If the organization protects stored data but ignores transmission risk, it is leaving a major part of the information life cycle insufficiently defended. Data at rest raises a different, but equally important set of concerns because organizations store enormous volumes of information long after the original transaction or task is complete. Files remain on laptops, records stay in databases, snapshots sit in cloud storage, and backup media may preserve historical data for months or years. If those storage locations are lost, stolen, accessed improperly, or exposed through weak permissions, unencrypted information may be immediately usable to whoever obtains it. Encryption helps reduce this risk by protecting the content even when the storage medium is no longer under trusted control. This is one reason encrypted laptops, protected mobile devices, secure storage volumes, and encrypted backup sets are so often treated as best practice. The protection is especially valuable for portable systems and removable media because physical loss is common and often happens outside tightly controlled environments. For auditors, data at rest encryption often leads to practical questions about scope, coverage, exceptions, recovery, and evidence. The goal is not simply to confirm that some devices are encrypted, but to determine whether important data is consistently protected according to risk and policy. Encryption also plays a role in identity, trust, and authenticity, even though those ideas are sometimes covered more deeply in later discussions about certificates and infrastructure. At a basic level, encryption-related methods help systems confirm that they are communicating with the right party and help users trust that a connection has not been quietly redirected or manipulated. This matters because confidentiality is only part of the broader trust problem. If users are connected to the wrong site or system, protected communication alone does not solve the issue. Organizations therefore use encryption not only to hide content, but also to support secure sessions, trusted exchanges, and confidence in digital interactions. For a beginner, it is enough to understand that encryption is part of a broader family of controls that helps make digital communication dependable. It protects content, supports secure exchange, and works alongside other mechanisms to reduce impersonation and tampering risks. This broader view is useful for the exam because it helps you see encryption not as an isolated technical feature, but as one of the building blocks that supports secure operations across modern business environments. Of course, applying encryption well involves trade-offs, and strong security decisions usually require balancing protection with performance, usability, and operational complexity. Encryption can add overhead, affect application design, complicate troubleshooting, and create dependence on proper key recovery procedures. Users may not notice this directly when controls are implemented smoothly, but administrators, developers, and auditors need to understand that stronger protection often brings added management responsibilities. A rushed design may encrypt data without ensuring that systems can still recover properly after an outage, or it may protect files so rigidly that normal operations become difficult and employees search for workarounds. That is not an argument against encryption. It is a reminder that good control design should be practical as well as protective. A mature organization plans for these effects by defining responsibilities, testing recovery, documenting exceptions, and integrating encryption into broader governance. The best controls are not just technically sound, they are also sustainable over time, which is a key concern in audit work where effectiveness matters more than impressive language and policy statements. From the audit perspective, data encryption is not evaluated only by asking whether it exists. Auditors look at whether the organization has defined when encryption is required, whether sensitive data has been identified, whether keys are managed appropriately, whether exceptions are approved, whether devices and storage locations are covered, and whether processes support recovery without undermining confidentiality. They may also look for evidence in policies, standards, system settings, key management records, incident reports, and control testing results. This is where beginners can see how security and audit come together. Encryption is not just a technology choice. It is also a governance decision, a risk treatment, an operational dependency, and a source of audit evidence. If an organization says customer information is protected, the auditor wants to know how, where, under whose responsibility, and with what assurance that the control remains effective over time. That mindset helps turn the topic from abstract protection language into something much more concrete and testable, which is exactly how CISA students should learn to think about it. Data encryption should feel much more grounded in everyday business protection and much less like a mysterious specialty reserved for mathematicians. At its heart, encryption is a way of reducing the value of exposed data by making it unreadable to unauthorized parties, whether that exposure happens on a lost device, across a network path, inside a backup set, or in a storage system that should never have been accessible. The most important lessons are that encryption supports confidentiality, that it depends heavily on sound key management, and that it works best when guided by risk, classification, and layered security rather than treated as a standalone fix. For a CISA learner, that is the practical foundation worth remembering. Organizations use encryption because data is always moving, always being stored, and always carrying business value. And when that value needs protection, encryption becomes one of the clearest and most effective tools available within a well-designed control environment.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.